My name is Meredith Kirk, and I am a chemistry teacher at Carnes High School. The handout that accompanies this video can be found on the KCS website under the Student Resources tab. This is Activity 3 for Chemistry Part 1. If you are having issues viewing this video, here are some helpful hints. And today we are going to learn about the characteristics of gases. We are going to start off with a video.
Marshmallow and a peep on a clean plate, put in a Del jar, hooked up to a vacuum pump. Flip it on. They expand it as much as they will. So the vacuum pump at work. Here's the fun part though. Turn it off. Close the valve. Disconnect. Here we go. There's our peep and marshmallow afterwards. Good stuff.
The video you just watched exemplifies Boyle's law, which relates pressure and volume. Boyle discovered that doubling the pressure on a sample of gas at constant temperature reduces its volume by 1/2. As one variable increases, the other decreases. Tripling the gas pressure reduces its volume to 1/3 of the original volume. This image shows what you saw in the video with the peep and the marshmallow. As pressure increases, volume decreases, and as pressure decreases, volume increases. Units are going to be very important when we begin the mathematical process of Boyle's law. Volume will be measured in liters or milliliters. Pressure will be measured in atmospheres, kilopascals, millimeters of mercury, or even torr. If you need a refresher on how to do conversions, please look at the reference sheet located at the back of your student handout. STP stands for standard temperature and pressure. Scientists use standard conditions for pressure and temperature. For temperature, we use 273 Kelvin, and for pressure, we use 1 atmosphere. The mathematical equation for Boyle's law is P1V1 equals P2V2, where P1 is your initial pressure, V1 is your initial volume, P2 is your new pressure, and V2 is your new volume. If we are given 3 of the 4 values, then we are going to solve for the 4th value. Let's start off with a word problem. A balloon filled with helium gas has a volume of 500 milliliters at a pressure of 1 atmosphere. The balloon is released and reaches an altitude of 6.5 kilometers, where the pressure is 0.5 atmospheres. Assuming that the temperatures remain the same, what volume does the gas occupy at this height? So let's start with what we're given. Let's break the word problem apart. I'm going to pick out important information. V1, we were given 500 milliliters. For P1, we were given 1 atmosphere. For P2, we were given 0.5 atmospheres. So that lets us know what we need to solve for, the only variable we have left, which is V2. So let's start doing some math. We're going to always start off with our equation, and then we're just going to plug and chug. So let's start off with our equation, which we know is P1V1 equals P2V2. When I plug and chug, I'm going to plug in 1 for P1, 500 for V1, 0.5 for P2, and then we are solving for V2. So let's simplify some of this math. When we simplify, we end up with 500 equals 0.5 V2. Well, I want V2 to be all by itself. In order for that to happen, I must divide by 0.5. When I divide 0.5 divided by 0.5, it ends up canceling out. I am finally left with V2 equals 1,000 milliliters, and there's your answer. So let's start off Charles' Law with another video.
Time for a science life hack. You've been playing ping pong, someone gives it a slam, and you get a big ding in the ball like that. Just can't play with it anymore, bounces everywhere. How do you fix it? Easy. Get some hot water from the kettle, pour it into a glass. Don't burn yourself. Put your ball in the water, push it under with a pair of scissors, like this. Wait 5 seconds, and bingo! Put your ball in the water, push it under with a pair of scissors, like this. Wait 5 seconds, and bingo! The hot water has heated up the air's expanded and pushed out the dent, and now you're back to playing ping pong. Life hack with science. Bye for now.
The video you just watched exemplifies Charles's law, which relates volume and temperature. Charles's law states that the volume of a fixed mass of gas at constant pressure varies directly with the Kelvin temperature. Kelvin is going to be vitally important. And remember, for every degree C, we're going to add 273. This image shows what you saw in the video with the ping pong ball. As volume decreases, temperature decreases, and as volume increases, temperature also increases. This is the mathematical equation for Charles' law. V1 over T1 equals V2 over T2, where V1 is your initial volume, T1 is your initial temperature, V2 is your new volume, and T2 is your new temperature. Now remember, temperature always has to be in Kelvin, which means we're going to use the equation located down at the bottom of the screen. K equals 273 plus degree C. So let's begin with another word problem. An aerosol can that is kept at 25 degrees Celsius occupies 0.50 liters. Directions on the can warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius. If the temperature is increased to 52 degrees Celsius, what will the volume be, assuming the same pressure? So let's start with what we're given. Again, we're going to break down the word problem and pick out the important information. T1, we were given 25 degrees Celsius, but remember, for every degree C, we're going to add 273, which means T1 is actually 298 Kelvin. V1 is 0.50 liters, and T2, we were given 52 degrees C, but remember we have to convert to Kelvin, so 325 Kelvin, which means we know what to solve for because we only have one variable left. Therefore, we are solving for V2. So let's do some math. We're always going to begin with our equation, and then we're going to plug and chug. So this time it looks a little bit different. I plugged in 0.50 for V1, 298 for T1, V2 we are solving for, and then I plugged in 325 for T2. This time we're going to have to cross multiply, which means I am going to multiply 298 times V2 and 0.50 times 325. When I do this, I get 298 V2 equals 162.5. I now need to get V2 all by itself. In order to do this, I'm going to divide by 298. When I do this, my 298s with V2 are going to cancel out. and I will be left with 162.5 divided by 298, which means V2 equals 0.55 milliliters. Gay-Lussac's law relates pressure and temperature. Gay-Lussac's law states that the pressure of a fixed mass of gas at constant volume varies directly with the Kelvin temperature. Therefore, as temperature increases, pressure also increases. This image shows an ice bath on the left and boiling water on the right. In the ice bath, you can see as temperature decreases, the pressure also decreases. And in the boiling water on the right, you can see as temperature increases, the pressure also increases. The mathematical equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. Now remember, temperature always has to be in Kelvin. For every degree C, let's add 273. So let's start off with a word problem. The gas in an oxygen tank is at a pressure of 3.00 atmospheres at 25 degrees Celsius. What would the gas pressure in the can be at 52 degrees Celsius? So let's always start with what we're given. We're breaking this word problem apart. We were given P1 as 3.00 atmospheres, T1 as 25 degrees Celsius, but remember we have to convert to Kelvin. So, therefore, T1 is 298 Kelvin. T2, we were also given in degrees Celsius. We have to convert to Kelvin, therefore 325 Kelvin. So we know what we're solving for because we only have one variable left. We are solving for P2. Let's do some more math. We're going to always start out with our given equation, and then we are going to plug and chug. So, in order to get P2 all by itself, let's cross multiply. When I cross multiply, I end up with 298 P2 equals 975. In order to get P2 by itself, I must divide by 298. When I do this, that allows both of my 298s to cancel out. Therefore, I am left with 975 divided by 298. This leaves me with P2 equals 3.27 atmospheres. And there's your answer. Let's watch one last video.
760. Gewonnen hat Herr Dr.
The video you just watched exemplifies the combined gas law. The combined gas law expresses the relationship between pressure, volume, and temperature of a fixed amount of gas. This combines Boyle's law, Charles's law, and Gay-Lussac's law all into one mathematical equation. The mathematical equation is P1 V1 over T1 equals P2 V2 over T2. Now remember, temperature has to still be in Kelvin. Let's work a word problem. A helium-filled balloon has a volume of 50 liters at 25 degrees Celsius and 1.08 atmospheres. What volume will it have at STP? So here is where you need to remember what STP stands for. STP stands for standard temperature and pressure. Standard temperature is 273 Kelvin and standard pressure is 1 atmosphere. So let's break down this word problem and write down what we are given. We were given V1 as 50 liters, T1 as 25 degrees Celsius, but remember, for every degree C, we have to add 273, so 298 Kelvin. P1 is 1.08 atmospheres. T2, we've already talked about, is 273 Kelvin, and P2, we also already talked about, is 1 atmosphere. So we know what we need to solve for because we only have one variable left, which means we are solving for V2. Let's do some math. We're going to start with our given equation, and then we are going to plug and chug. So now, I need V2 all by itself. We're going to start off by simplifying the top of your equation. When we simplify, we end up with 54 over 298 equals V2 over 273. So now let's start solving like we were before. Let's cross multiply. When we cross multiply, we end up with 298 V2 equals 14,742. I want V2 all by itself, so I'm going to divide by 298. When I do that, my 298s cancel out, and I am left with 14,742 divided by 298, which means V2 equals 49 liters. And there's your answer. Alright, now it's your turn. Complete the practice problems at the end of your student handout. Once you have done that, you're ready for part 2 of Activity 3.
My name is Andrea Heverdays, and I teach chemistry at Bearden High School. The handout that accompanies this video can be found at the KCS website under the Student Resources tab. This is Activity 3 for Chemistry, Part 2. If you have issues with this video, here are some helpful hints. And today we're going to be learning about the ideal gas law. We're going to start with a video.
Well, as the weather gets colder, you might notice a tire pressure warning in your car lighting up.
It's common as winter settles in. So why do our tires go flat in cold weather? Good question. Heather Brown explains the science and how to ensure you have a smooth ride.
Excuse me, ma'am. Hey there.
Hey, how you doing?
Hey, so do you mind if we check the pressure in your tires?
Yes, you can.
I'm going to be on TV, ain't I?
I hope so.
I do have a tire gauge if you need a tire gauge, but
Oh, you're prepared. Okay. The driver's getting gas. Look at you, right on the dot. So we're looking for 35 PSI at Steve's Auto World in Maple Grove. Okay, yep. You're low. Got an extra service today. Oh, yeah. You're right on, right at 35. Just because the light comes on in our car doesn't mean that our tires are leaking air.
Yeah, it just means that they fluctuate.
Nate Anderson owns Steve's.
They're kind of like a balloon where when it gets colder, it kind of shrivel up in strength.
That's because cold air is denser. So for every 10-degree drop in the temperature, tires will lose 1 to 2 pounds of pressure. What's the problem with low tire pressure?
You get worse fuel economy. It also wears out your tires faster. You get worse traction on ice.
Can you feel a difference in the ride?
Yes, I can. It rides rougher.
Since 2007, all cars are required to have tire pressure monitoring systems.
I don't check it very often because I have a dummy light.
But if you have an older car, check every few weeks. You could probably use a little air. Okay. You can find the right pressure on the inside of your driver's side door. Your door's telling us 33 PSI. Right. What range do you need to be in?
Usually your tire light gives you about 5 PSI.
And most air pumps have a gauge on them. All right. We're good to go. You thought we just stood around and interviewed people, huh?
yeah.
No, I was like, what the heck they're doing right there?
Thank you.
Yeah. Heather Brown. Full service operation here, huh? WCCO 4 News.
So, in our previous section, Mrs. Kirk explained how pressure, temperature, and volume affect the behavior of gases. But as the video shows, adding more gas to your tires increases their pressure. It also increases their volume. And so we need to measure the amount of gas as another factor that affects gases. So to measure the amount of gas in chemistry, we use moles. The ideal gas law is the mathematical relationship between pressure, volume, temperature, and the number of moles of a gas. It's on your reference sheet and also here. PV equals nRT, where P stands for pressure, V stands for volume, N stands for the number of moles. Again, M is taken by mass. R is our universal gas constant, and T is temperature in Kelvin. The R, that universal gas constant, on your reference sheet has many units, as you can see. I've listed one here as 0.0821 liter atmospheres per mole kelvins. This means that our pressure must be in atmospheres, our volume must be in liters, that our moles must be in moles, and that our temperature must be in Kelvin to match those units of R so that our algebra works out. So let's start with an easy problem. What is the pressure in atmospheres exerted by 0.5 moles of a sample of nitrogen gas in a 10-liter container at 298 Kelvin? So we're going to start with what we're given. We're given the number of moles, that's our N. We're given 10 liters, that's our volume. And we're given 298 Kelvin, that's our temperature. Remember that we're always given R since it's a constant and it's on your reference sheet. Now we know what to solve for, so we have to find pressure. So let's do some math. We're going to start with our formula, PV equals nRT. To solve for pressure, we needed to get that volume divided to the other side of the equation. So when we rearrange it, pressure equals nRT divided by V. Now we just have to plug and chug our numbers. Our moles times our R times our Kelvin temperature divided by our volume gives us a pressure of 1.22 atmospheres. Now let's try a harder one. Sometimes you have to do a lot of conversions before you even start the problem. For example, at what Celsius temperature does a 54 milliliter tank at 745 torr that contains 0.62 grams of nitrogen gas? So this is going to be a lot. We're given in grams. Grams is going to be our amount of substance, but we're going to need to convert that to moles to use our formula correctly. Our volume was given to us as 54 milliliters, but we're going to need to convert that to liters. Our pressure was given to us as 745 torr, but to match our R value, we're going to need to convert that to atmospheres of pressure. And again, we're always given R. This time we're going to be solving for temperature. So to convert is annoying, I know, but here we go. Let's start with volume because it's the easiest. Knowing that we have 54 milliliters of our tank, we can convert those milliliters by dividing by 1,000 or by moving the decimal place over to the left 3 times. When I divide by 1,000, I'm canceling out my units of milliliters to get liters, which will be 0.054 liters of gas. For the pressure, 745 torr needs to get converted to atmospheres. Those conversion factors are again on that reference sheet. If I divide by 760 torr, which equals 1 atmosphere, the torrs will cancel and I'll be left with my atmospheric pressure. Lastly, we need to get moles. Starting with 0.62 grams of nitrogen gas, I need to divide by its molar mass to get the moles. Nitrogen weighs 14 on the periodic table, but being a diatomic molecule, 14 plus 14 makes nitrogen weigh 28 grams per mole. The grams will then cancel, and I will then have my moles of gas. Using these values, I will then use my PV equals nRT equation, and I need to rearrange it to solve for temperature. To get temperature alone, I'm going to divide by N and R to the other side of the equation. So now my equation is pressure times volume divided by the number of moles times the universal gas constant. Now we just plug in the numbers that we just finished converting. My pressure in atmospheres times my volume in liters divided by my moles times my R value. This gives me 29 Kelvin. However, the question asked for the temperature in Celsius. So to go back to Celsius, just subtract 273 to get negative 244 degrees Celsius. The ideal gas law can also just be asked to find the mass of a gas. When finding mass, you have to remember that mass is an amount, and we can get it from the ideal gas law by solving for N. So in this question, it says what mass of chlorine in grams contained in a 10-liter tank at 27 degrees Celsius and 200 kilopascals of pressure. So we're going to start with what we're given. We're given a pressure in kilopascals, we're given a volume of 10 liters, and we're given a temperature of 27 degrees Celsius. And remember, for every degree C, add 273. That will give us our Kelvin temperature. Our R is constant. And then N is what we need to solve for. However, we're going to need to convert it to mass at the end. So instead of converting this time, let's just change our R value. Again, there's two R values on your reference sheet. One in atmospheres of pressure and the other one in kilopascals of pressure. So if we start with our formula, PV equals nRT, this time solving for moles, we need to divide by R and T on both sides to get N by itself. This rearranges our equation to where pressure times volume is divided by R times T. Now we're going to plug in our values. This time we're going to keep our kilopascal pressure as 200 times our volume of 10 liters divided by a different R, 8.31. That value represents the kilopascal pressure, and then times our Kelvin temperature gives us our number of moles. Then we need to convert those moles to mass. To do that, we'll multiply by the molar mass of chlorine gas, where that chlorine is Cl2. Chlorine weighs 35.5 grams per mole, but I need 2 of them, so that's 71 grams per mole. When my moles cancel, I am now left with my answer of 0.57 grams of chlorine. Now you try. Thanks for watching.